Yeah, so this next presentation, oh, sorry, will be given by Hyeeun Jang, and it'll be on modeling real-world applications of ODEs with Python.
Uh, Good afternoon. I'd like to share how I used to use the Python to help the student understand the basic models. My focus is not solving the equations, but helping students see meaning behind the equations. In my OD class, I noticed something students can solve the differential equation well they were interested in, but they often not interpret the model or what happens if parameter changes. So my question is, what does this parameter means? What happens if we change this number or that number and the solution behavior? So today I brought two models, logistic growth and underdamped mass spring. Here is a basic model, the logistic growth model. And the simple idea is the growth is almost exponential when the population is small, p is small. And then R stands for growth rate, RK, carrying capacity. But growth slows down when the population get close to carrying capacity. I might ask questions. If I change carrying capacity, if I change carrying capacity, what happens if I change the natural growth rate? What will change? So here is an example. I give them the natural growth rate and then the carrying capacity. And then we were able to solve this equation by hand. And also I gave the initial condition, the value of initial condition 10. So we got this special solution. Using this, the solution we just got, we were able to the activity just changing our the what happens. So first I fixed the K and then only R changes and then eventually we will see R the natural growth rate controls how fast the population moves towards equilibrium, but that does not change the equilibrium level itself. So I'm going to share the Python that I used during the last semester with my student. I exactly copy and paste when we did together by hand. So the same number, same initial condition carrying capacity, because my target is for beginners, Python beginners. Most of the students are really beginner, and a few students even don't know how to use the Python. So I tried to make a really simple code as possible. So everything given conditions I put here, so we were able to make this in a second. And in the C also, we solve this equation for constant in algebra. And then P is a general solution we already got in traditional lectures. So we only need the simple code for this interpretation, the solution behavior, and then the PLT plot, and then these code are may or may not necessary. So they only need these key necessary code with the show. And then my focus is we just change R here. And then we're gonna run. I'm gonna a little bit zoom in here. Okay. So given the R is equal to 1, this would be our original value. But what happens if it is a little bit the slower than the 1? So they eventually move towards equilibrium because equilibrium is P is equal to 0 and then P is equal to carrying capacity, which is 100. Sorry. So eventually they uh, go over time towards the equilibrium 100. But what happens if R is equal to a little bit greater than 1, the 5? a little bit steeper than before. What happens 25? And then it's pretty much steeper, but equilibrium is still the stability does not change at all as we change the R because they eventually towards the 100, which is carrying capacity, and then X is equal to P is equal to 0 is unstable. So they will get equilibrium P0 unstable and Y equilibrium 100 is stable, and then are just to control how fast the solution, the behavior approaches to equilibrium without changing equilibrium value. So I gave them instructions. What happens when we change the R and then write down your thought, your idea using this print. Uh, I believe that I thought that the sprint command would be easiest one for beginner to show us uh, their result. And then I'm gonna go back to the activity number 2. So we just switch the role, we fix the natural rate, growth rate, and then we change the carrying capacity. You're already aware P is equal to 0, equilibrium 0 does not depend on any carrying capacity, but the second equilibrium K carrying capacity changes if K changes. So equilibrium level just moves up or down depending on the K. So I might ask them what changes when K changes. So eventually it is a long-term behavior when carrying K changes, the population level increases. So we just keep everything as it is. I will come back here and then only changes the K. What happens if your carrying capacity is less than initial value, which is 10? Says I want to set up just one. So it looks like really the decays, but that they eventually move towards equilibrium, K is equal to 1. But if they are really familiar with this basic code, I might be able to give them, I already gave them after 1 month. We can add this for an in command. So I give them 1, which is less than my initial value. 10 is exactly the same as initial value. Carrying capacity is greater than my initial value. And then this would be unnecessary. If I don't want, I can just eliminate it. And then eventually we will get a little bit zoom. So depending on different carrying capacity, yeah. But as we change the carrying capacity, the stability type does not change it at all. We still move towards equilibrium. When K is equal to 10, exactly the same as initial value, they doesn't change, the population doesn't change it at all. But what happens if K is equal to 1, which is very small, initial population is just a 10, is a larger than K we start from here, but it looks like exponential decay, but approaches to K is equal to 1. They may or may not really good for interpretation as K approaches to K grows higher than the before. But if I use this, the basic the code, it will help them understand the better. And then also, unlike R that only changes speed of approach, K changes the destination itself. I also brought another one that was also interesting to us under damped case of mass spring system. The motion oscillates and then decays at the same time. So student can see two effects, main two effects, their oscillation, vibration, and damping. Since the discriminant is less than 0, we call it underdamped. I would say this is lambda damping rate, omega 0. We define this, we use this notation, omega 0 natural frequency, omega d, and then damped frequency. And our general solution would be, I use the Euler formula. because this exponential terms affect their decay, the motion dies out because of this trigonometry. It affects oscillation. I gave them some parameter fixed initial location, initial velocity, and then we were able to compute this constant number as well by hand. And then we changed the beta. My activity was here, given the same model, we changed the damping constant to 0.5 to as beta increases, what happens? So the motion dies out the faster just by looking at this model or just by looking at just a solution may or may not be hard to interpret. So we use the Python using really, really simple code. So I will show you here exactly the same because I'm not gonna I'm not gonna make a real, I'm not gonna create a new definition. I'm not gonna derive the ODE how to solve it, but given the existing definition, I just plug this back into the definition rather than using lambda as a function and non as a function. I use the solution. I wanted to add something definition in one solution. That's why I use the definition here. If I don't want to use it for an in roof, I might be able to add here beta and then we just change respectively separately 0.5 and then 2, but I made a roof, but it'll be easy to understand over time, and this would be of course the final touches, so it may or may not unnecessary. So we change the damping constant, so 0.5, 2, and 4, 5, and then the compute. So they will get eventually easily understand when the beta becomes the large 0.5 through all the way through 5. You may use a linear space between 0.5 and then 5, but in other words, amplitude decrease more quickly. They might be able to interpret another way. The system loses energy more rapidly because uh, damping force is stronger. So oscillation becomes slower. So using the simple code, it helped the student better understanding. So in my classroom experience, spending even a small amount of time, 10 or sometimes 15 minutes, each week, each class Monday, Wednesday, Friday, class last semester, and computational modeling significantly improve student interpretation. They enjoy a lot and then conceptual understanding very well. So thank you.